Hi, welcome back to our next video on kinematic indeterminacy. In the last video, we have seen how we approach fourth method of analysis and distribution method of analysis. And in the video, we have truly defined what is kinematic indeterminacy. Here we have a different definition. We can say the kinematic indeterminacy is the number of unknown independent joint displacements required to define the space profile of a structure. Okay. For a planar structural system, if we consider a joint, there are two ways in which joint displacement can happen. That is, one is translation and another one is rotation. Now let's see the kinematic indeterminacy of truss first. For example, we have a simple truss given in this figure 1 where we have a symmetric configuration with respect to the load, geometry, and then the sub. When we apply a load at this joint C, let's say first the initial configuration given by this black line, and then when we apply this load P, what is going to happen? The truss will be displaced, which is given by this, that is the orange dashed line. So this joint comes down to this position. And because of the symmetry condition here, we can say the horizontal displacement of this joint is 0 and there is an unknown vertical displacement. But as such, for any other kind of loading or say if the truss is not symmetric, in general, we need to know these two displacements such as u and v. And these two will be independent and there is no need of any rotational degree of freedom here. So overall, we can say the kinematic indeterminacy in this case is 2. Okay. So once we know the joint displacements such as u and v, what we can do is we can determine the deformation of each member connected to this particular joint. And once we know the deformation of those members, we also can get to know the internal stress resultants. In this case, for a truss, the internal stress resultant is the axial force. And after knowing the axial force, we can also determine the reaction. So overall, we can say once we know this displacement, the analysis is complete as far as the strictest method of analysis is concerned. Right? And we'll also see what is going to happen at a pinch joint of a truss system. Toward that, we are considering this first figure in which we have a simple truss ABC, which when acted upon by this load P at this joint C, cause the displaced profile like this of the truss. Now, initially, this is the way this particular joint C will be. So we're just showing that here it is not appropriate to overlap this on top of that, but just to show the change in angles, we are doing that here. That is before deformation. This is how this joint C is. And from the displaced profile, we are taking this and overlapping here. So this is the manner in which the joint C will become after the application of load. Now the change in angle between the respective members will be given by phi1 and phi2. And we see that in a pin joint, these two are not going to be same. Okay, but if we take a frame, a typical rigid joint, these two values will be same. Okay, here they are not same. All right. And another important point is each member connected to a pin joint are free to rotate at this joint and they don't bend. Okay. So we can say truss elements do not suffer any rotational deformation. Okay. And these rotations are due to joint displacements at a pin joint. So if we know the joint displacements at a pin joint, we can also determine these rotations, but which are not of any relevance. Okay. So overall, we can say the strain that develops in a truss elements due to the change in members length. And once we know them, okay, that is, I mean to say, if you know the displacement of a pin joint, we can also determine the axial deformation. Okay, so all the information which are of concern in a truss element is the joint displacements, such as this. Okay, so if we align our global axis like this, so this plus this is what is required. So that's what I have given here. If we know the joint translation displacements in two perpendicular directions at each joint of a truss, the analysis is complete as far as the displacement method of analysis is concerned. Now let us consider a typical element of a truss like this. So AC is shown here. Before deformation, this is the position, after deformation, this is the position. So we see that these two joints AC gets displaced, and those translational displacements are characterized by U2 V2 and U1 V1 respectively. That is, U corresponds to, or U represents the horizontal displacements and V represents the vertical displacements. Now this is what happens for a typical member. Now if we consider this, that is, if we are characterizing the joint displacements by U and V respectively, we can see what happens with each of these members. So we have drawn here the member AC, member BC, and then this member AB here. So to characterize the joint displacements for each of these members, we will mark U1, V1, U2, V2 respectively. So that's what I have done for each member. We can see that at the end of, or the joints of each member, we are drawing these two degrees of freedom. So the question is, now we have total 12 of them. Does that mean 12 is the kinematic indeterminacy? No. Why? Because see, at every joint, the members connected to them should move along with the joint. That means this U2 and U2 dash can't have independent values. Okay, that's what I have given the definition. The unknown, I have missed unknown here. Please consider that unknown independent joint displacements. Okay, the number of them is the kinematic indeterminacy. So here for compatibility, this U2 should be equal to U2 dash and V2 should be equal to V2 dash. Only then the member will be intact at the joint even after the application of load. Such similar kind of conditions apply at other joints such as A and B as well. So here, if you consider joint A, this U1 should be equal to U1 dash and V1 should be equal to V1 dash. If we consider all such compatibility conditions, overall we can say we end up only with these 6 displacement degrees of freedom at joints such as A, B, and C. And even among them, all of them are not unknowns because this U1, V1, and V3 are known to be 0. Why? Because those correspond to the boundary conditions prescribed. Okay, that means we know that at a pin joint there is no possibility of horizontal vertical displacement, and similarly at a roller joint we know that there is no vertical displacement possible. So because of the prescribed boundary conditions, U1, V1, and V3 are known to be 0, and however these three values are not known. That is, we don't know what is the value of U3, we don't know what is the value of U2, and we don't know what is the value of V2. So in the displacement method of analysis, these three constitute the unknowns. Therefore, we can say the kinematic intensity for this stress configuration is 3. And in general, we can propose this formula, kinematic intensity equal to 2J minus R, where J is the number of joints and R is the number of reactive components. Why 2J minus R? Because we know that at every joint, two possible ways of translations are there. And from that, we need to also deduct those which correspond to the prescribed boundary conditions, which is related to the reactions. Okay, so overall we have 2J minus R. This enough. We will have a look at some examples. We have 3 examples here. So for the first configuration, there are 6 joints. Okay, 1, 2, 3, 4, 5, 6. So 2 into 6 minus 3. 3 corresponds to these 3 reactive components. Okay, so we have the kinematic intensity 9 for this stress. And the second, again, we have 6 joints, you can count them, and we have 4 reactive components. So we have 2 into 6 minus 4 equal to 8, which is the kinematic intensity in this case is 8. And finally, we have a compound truss here. In this case, we have 7 joints and then 3 reactive components. So use the formula, we see that kinematic intensity equal to 11. You can use the formula, otherwise what you can do is, as I have done here, you can mark the possible displacement at every joint and then sum them up. That's all. This is quite enough to understand the kinematic intensity of trusses. The next video we will see the kinematic intensity of beams. And one more important update here is, in the website we also have included another feature called Ask Us a Question. Okay, Ask Us a Question. So one can go there and submit a question which you find difficulty with solving. That means, for example, if you have a beam and then you don't know how to draw the SFT BMD, you can submit the question there and we will answer. Okay, we will answer. It can be anything related to structural analysis. Okay, so make use of this feature and learn along with us. Thank you so much for your passion listening. We'll meet in the next video.